server driven by this parameter called checkpoint segments. You heard Robert's talk earlier, he mentioned this briefly as well. Checkpoints happen one of two ways. They either happen because a certain amount of write-ahead log data has been written to disk, or they happen because some period of time has passed. Now that period of time defaults to 5 minutes in Postgres. So unless you change something, as long as something has been written, and I only add that caveat because there is an optimization that if you haven't written anything, it won't do a checkpoint because there is supposed to be two. If you've written anything at all, you will get a checkpoint at least every 5 minutes is the intention. And that's driven by a parameter called checkpoint timeout. Normally people don't need to change that at the beginning. You need to change it in a really busy system eventually. But what a lot of people need to change very early is checkpoint segments. The reason for that is what's called a write-ahead log segment in Postgres. These files and transactions get written to. They are 16 megabytes by default. And you can change that, but almost no one ever does, and it's probably not a good idea to play around with that number. So, unless you go really crazy, they'll always be 16 megabytes. The default value for checkpoint segments is 3. So that means that you will have to do a reconciliation of all of the data that you've got in RAM, in Postgres' shared buffer cache, and the operating system every time you've written 48 megabytes worth of data to disk. That's not very much anymore. Again, it goes back to if your server has 256 megabytes of RAM, sure, 3 is a completely reasonable value. Otherwise, it's probably not. I normally will bump this number up to just 16 reflexively. Giant servers, I've set it to in production as high as 256 before. When you're actually loading new data into the server, even more ridiculously high values are completely reasonable. The main trade-off to realize here is, first off, this is not going to drive your checkpoints completely because the timeout is still in there. At some point, checkpoint segments gets big enough that you tend to have the checkpoints every 5 minutes based on the timing. At that point, further increases to it don't really buy you anything. The main trade-off here is, however big this number is, affects two things. First off, it affects how much disk space is used by the write-ahead log segments that get stored up. And these are these things that are stored in a PG underscore xlog directory in the database. So transaction logs, xlog, write-ahead log, these are all the same things we're talking about. The bigger you make this number, the more disk space will get used by those things. So if you just go completely bonkers with it, you set a big timeout too, particularly in the case where you put the write-ahead log information on a different drive, you can discover actually there's a potential for it to run out of disk space. That's not normally the main driver though. The main driver is when your database crashes for some reason, unexpectedly, it has to be restarted again, maybe a weird power outage, maybe someone tripped over the cord, maybe it just crashed because of a bug, who knows. When the server starts back up again, it goes back to the previous checkpoint and says, okay, let me look at all of the write-ahead log data that's happened since the last checkpoint and make sure everything's reconciled and consistent on disk and I'm happy with the state of things. How long that process, which is called recovery, takes is proportional to how long it's been since the last checkpoint. So if you make checkpoint segments really high, and to make the problem even worse, if you start changing the timeouts and stuff like that, you can get into a situation where that recovery time is actually significant. And it can take many minutes for that to happen. I have had post-crash recovery take 4 hours before on a system that, because of some misconfiguration issue, had 8,000 write-ahead log segments it had to replay when it started out again. So replay time of write-ahead log data. It's not funny. It does pile up. It's normally not a problem for people. It's just, this is why you don't want to go too crazy with just going, well, it gets faster if I increase this number, so let's just keep making the number big and this is the brief intro to checkpoint. The third thing that almost every site ends up setting is this thing called effective cache size. Effective cache size doesn't allocate memory. It's not, you need to be concerned about whether you're going to run out of RAM if you make it too big. Effective cache size is used for internal decisions about whether or not the database optimizer thinks that it will be able to fit an index into RAM. So when it's deciding how expensive is it to use this index, it looks at how big the index is relative to this number, and it makes some decisions about it. It's got this scary method it uses based on some mathematical foundations. In practice, this ends up impacting some types of query plans where you're using inner index scans on joins. You know, there's a couple of technical spots it pops up, but the idea is if you've got this set to default, which is a completely trivial 128 megabytes, Postgres will think that any index bigger than 128 megabytes is probably too big to fit in RAM, and therefore it may not want to use it. That's probably not true. Again, unless you're running Postgres on a really cheap phone. Normally, the idea here is you set an effective cache size. The reason why the concept is effective cache size is since Postgres uses both its internal caching as well as the operating system caching, the idea is this is how big the operating system cache underneath of this thing is approximately. And that's normally on most dedicated database servers that ends up being around 3/4 of RAM. So that's the starting values people will put on a brand new server. If you want to fine tune it to actually be more accurate, what you do is you start the server up, you start your application, you put some non-trivial load on it, and you actually look at how big is the amount of data that is free or being cached by the operating system right now while you're running that workload. You add them together and they have an effective cache size number. The 3/4 number is just extracted from a lot of people have done that at some point and went, it's normally around 3/4 of RAM. This also makes sense when you consider that the old guideline for shared buffers was 1/4 of RAM. If you're using 1/4 of RAM as dedicated memory to Postgres, it's going to be about 3/4 stuff and 1/4 stuff. The final parameter that's in the really critical and completely wrong by default, and you have to be careful about it, category is this thing called workmen. Workmen is also not a explicit allocation of memory. If you set workmen to a value, it doesn't go allocate that memory by default. It uses it for a different type of computation. So what happens is there are a couple of types of operations that Postgres will do where it needs working memory in order to do something. The two most common somethings are if you're sorting data, it needs to store the information that it's sorting somewhere. And this parameter actually used to be called sortmen in older versions of Postgres because that was almost exclusively what it was used for. The other thing that it gets used for is becoming increasingly more popular starting in 8.4. Which is it'll use it for making decisions about hash tables. Hash tables are the compact representations of the important parts of some query that you're running that are needed to make decisions about things. So a hash table might, for example, contain the list of primary keys for the table that you're joining to another table. You don't really need to store the whole table if the only thing you were going to use it for was deciding whether or not there's a matching join. You can just save a hash table instead and save yourself a bunch of trouble also get used for